Thank you very much. Happy to still be here. I just want to continue basically on the themes of the past two talks. So we introduced this category of definable analytic spaces, talked about some applications to period images and Hodge theory. Now I want to continue in that thread. And so let's start by getting a little bit more geometric. So for those who sort of aren't in the field, which includes myself to a large degree, what's sort of a general thrust of the field? So you should think of this as like a moduli space of algebraic variety. So the fiber of this map X to M are some interesting classes of varieties that you want to study, curves, even varieties, these, whatever. And what you want to do is you want to compactify this family. You want to extend it to some X bar to M bar, where M bar is proper. You want various nice properties to hold. There's often many ways to compactify it. You're looking for a good one. So one thing you might want is some sort of geometric conditions. So you might ask for the fibers to be sort of only mildly singular or some particular form. You might ask for the total space to be smooth, various other things you can impose. From a moduli perspective, what you would like is for the fibers, even of the boundary that you added, to have some geometric properties, in particular to have an interpretation as some degenerate versions of the fibers you were studying before. So we'll see some examples of this, and one of the most famous examples is if you look at the Baily-Borel compactification of Mg. So Mg parameterizes smooth projective curves, and then you can interpret and compactify it in such a way that it parameterizes stable curves. You still have a nice interpretation. And something that's still good, but not as good, is if you can't extend the family, but maybe you can still interpret the points of the compactification in some sort of moduli theoretic way in terms of degeneration. This is a very sort of vague overview of what one might want. And our goal in this talk is basically along the same thrust we've been going, which is to study moduli in Hodge theory. Now we want to study compactifications as well of image to period maps using certain Hodge theoretic information. So that's kind of the thrust of what we're going to be talking about today. So as an example, sort of a very motivating example for us in particular, because the Hodge theory governs things extremely rigidly in this setting, let's talk about abelian varieties. So the simplest case is elliptic curves. And we're going to think of a degenerating elliptic curve. So an elliptic curve just over a formal disk here, C adjoint T, Laurent C adjoint T. And after perhaps making a ramified base change, you can always extend this elliptic curve over the sort of puncture. So to map algebraically, mapping to power series, you take the power 1 over n, in such a way that the fiber, I don't know what my G is not compiling, I swear I checked my G's, but the central fiber is singular and the smooth part of it is just Gn. So you have the group law sort of preserves. You have elliptic curves, and now in the degenerate way, you get the multiplication group at the bottom. And here's an example, a very concrete example, where you have an elliptic curve, and then at t equals 0 becomes a multiplicative group. So in that sense, this is a little bit silly because it's so straightforward. But if you look at the moduli space of elliptic curves, y1, you can add a point at infinity. You can compactify it P1, stack it P1, and you can think of this extra point as sort of the degenerate elliptic. Okay, so let's extend this now to abelian varieties, where you have a lot more that. So given an abelian variety, once again, doing the same kind of thing, you can extend in such a way that the connected component of the smooth locus becomes a semi-abelian variety. So it's going to be an extension of some abelian variety here. I don't know why I didn't write that goes to 0, but that's also there. And the torus component over here. And then you also have to choose sort of your moduli space, what information does it want to record when you compactify it. And in this case, the Baily-Borel compactification, which is going to be our model in the general Hodge theoretic framework for the kind of compactification we want to make, records precisely this abelian part. Okay, so there's more information, there's extension data here, which you could also try to record, and people know how to do that in various ways. Our model will be, we're going to throw away this T, we're going to throw away the extension data, we're going to just keep track of this B. And so in the boundary, we're going to have abelian varieties of varying dimensions, though. And so we're going to end up, I'm not constructing it for you, but once you construct it, you get a compactification whose points are sort of the union of the moduli space of abelian varieties of dimension going from 0 to G. Okay. So we're going to try to understand this Hodge theoretically. Given an abelian variety of the complex numbers, you have this norm vector space, you can think of as, depending what you're doing, either determinant, so top wedge powers, or you can determine it here, of global one forms, or just global top forms on your abelian variety. And this is not just a vector space, but it has a natural norm coming from the Hodge method, because this H naught A omega G is the sort of highest piece, the lowest dimensional piece of the Hodge filtration, or the cohomology of your abelian variety. So you get a norm vector space, and in fact, you can extend this, you do this construction in a relative sense, to a normed line bundle on the moduli space of abelian varieties. So if you specialize this to any point corresponding to an abelian variety A, it becomes naturally isomorphic to this norm vector space. And then the really cool thing is that the Baily-Borel compactification you can interpret intrinsically. So we made a bunch of choices when constructing it, but you can actually construct it just from knowledge of AG and not making any choices. In this way, you can look at cusp form, the ring of cusp forms, which is you look at the all global sections of powers of the Hodge bundle. Now there might be too many if you just allow all sections, like for Y1, you're going to get a ring that's way too big. So to make these finite dimensional, we're going to use the norm, and we're going to insist that they have moderate growth at infinity. So the Hodge metric grows subpolynomially as you go to the boundary. And as a just observation, note that you can say this without actually specifying what the boundary is, right? You can sort of restrict to any curve, for example, and say that it grows subpolynomially there or something. We talk about this purely in terms of the interior. And then, sorry, this should be AG Baily-Borel. The Baily-Borel compactification is the projectivization of this, the product of this thing. We're covering intrinsically in this way. Okay, and the idea is going to be to try and emulate precisely this construction for moduli of Hodge structures. So we want to record through compactification some kind of generations of Hodge structures. So first, let's ask, given the generating family of Hodge structures, what kind of stuff exists at the boundary? So let me tell you some information that exists, and we're going to just restrict ourselves to the case of varying over a one-dimensional disk, but you have a similar, more complicated story over polydisks. So first of all, you end up getting this weight filtration on your lattice, in your variation of Hodge structures, and you still have this complex filtration. I'm jumping ahead a little bit, aren't I? Oh no, this is the definition. Sorry, excuse me. Before I tell you what exists, we're going to talk about mixed Hodge structures. So a mixed Hodge structure is a lattice with not just a Hodge filtration, but also this kind of increasing weight filtration and some slightly more complicated data, such that if you look at the graded pieces, then induced by this Hodge filtration, you get a weight K Hodge structure on the kth graded piece. So it's a sort of, that's why it's called mixed, because it mixes up a bunch of Hodge structures of various weights. So if you have this variation, what can you do? Well, first of all, if you tensor with O, you can extend to a vector bundle, you take a lim extension to a vector bundle over the whole disk, and the filtration will also extend. Yes.
And the GERD K is referring to the weight filter. Is that right?
I'm sorry? The weight, that's right. The GERD K is referring to the weight filtration. Yes. So you can extend to the boundary with this vector bundle. The weight filtration extends as well. And if you look at what you actually get on the boundary, the fiber, you get a mixed Hodge structure, which is not quite canonical. We know how non-canonical it is. But regardless, the important thing for us is that if you look at the kth graded piece, you get canonically a weight K Hodge structure. So the important thing for us is that in some way, once you extend, you generate a pure Hodge structure to the boundary, you get sort of for every K, well, for finitely many K, a weight K Hodge structure that it degenerates to. So to relate this back to our concrete example of abelian varieties, once you degenerate to this kind of narrow model, you get a mixed Hodge structure of weight 2, and there's nothing beyond weight 2 or under weight 0. So the weight 2 pieces are simple. They're just these sort of Hodge state structures, Z0 to the n. And the weight 1 piece is just given by this abelian variety, by the first homology of the abelian variety. So in a very precise sense, if you want to record the moduli of the graded Hodge structures in the boundary, you exactly want to keep track of this B, which is what the Baily-Borel compactification is doing. Okay. And I want to mention, I'm not going to talk about this in the talk, but if you want to record more, so this extension data, various pieces of the extension data, then that and more is provided by the theory of toroidal compactifications for AG and for Fourier varieties. And in general, there's some work of Kato, Mikayama, and Usui to set this up in general. And Deng and Robles have recent work in the general case, in certain instances, constructing this kind of toroidal compactifications as well, which I believe I'm talking about this conference. But I won't talk about that anymore in this talk. So let's get back to period images. We have a proper period map from usually a smooth X. And we look at the image side D mod GZ, and we call phi of X period image. Now, you can also consider this sort of intrinsically, now that we have the theory of definable analytic spaces, as you have this D mod GZ, you can look at subvarieties of it, which are definable, analytic, closed, and algebraic. So algebra have admits some algebraic. Regardless, we're going to look at these things. And the main theorem, this is joint work with Baker, Philippi, and Maury, is that we're going to construct a functorial Baily-Borel compactification of all of these period images. It's going to have some properties. So first of all, it's going to have this extension property. So if you have any log smooth Z and Z bar, so both Z and Z bar are smooth, and the complement is a normal crossing divisor, locally looks like a bunch of hyperplates, then any map to, I don't know, it's T, any map from Z to Y extends to a map from Z bar to the Baily-Borel compactification. So it's some sort of universal compactification. Oh my God, the typos keep coming. If you look at Y degree the compactification, you remove Y, then you have a finite stratification of the boundary, just like in the AG case, where each piece of the boundary admits a quasi-finite period map. Okay, so you can interpret all the pieces of the boundary in also some theoretic sense, though it's not quite as canonical as might hope for at the moment. I'll say something about why. And finally, you can also construct this intrinsically. So there's the analogous bundle of the Hodge bundle, which in this case is the Griffiths bundle. So you take all the Hodge pieces, you take the determinants, you tensor them all up. That turns out to be the relevant bundle of the study. And once again, you have a Hodge metric on this guy. So you can look at moderate growth sections just of the interior. You get some graded ring, you take its proj, and you get this Baily-Borel compactification. So I said last time we have some analog of modular forms or cusp forms, and you can think of this as that analog. Okay. Yes, one would hope for, like in the case of AG, we would have some universal compactification, but as is typical with Hodge theory, you sort of have no universal moduli space because it's not algebraic. We sort of know you can't compactify it in some sense, because if you could, they would have to be algebraic. It's not quite true, but it's close.
The complement of Y to B has the dimension greater or even.
No.
Oh, the question. No, okay.
The question was, is the complement of Y inside the Baily-Borel compactification of co-dimension of these two? But even for elliptic curves, you get points, right?
Except in X.
I'm sorry?
Except in X.
Oh, you mean for Shimura varieties?
So more like for the general period, when the complement dimension created co-dimension created.
In what generality?
Yeah. So I mean, for Shimura varieties, you know when co-dimension is one.
I see.
And
Oh, can I answer the question? Oh, I see the question. Sorry, I thought you were telling me here. I haven't thought about it. Sorry, yes, seems a question.
as long as I'm asking, said you didn't want to talk about toroidal compactification.
Yeah.
How do these have toroidal compactification? Or toroidal resolution?
Do our Baily-Borel guys?
Yeah.
Oh, we don't know anything like that, no. I mean, Deng and Robles have in some cases, here they give you a toroidal, and then by our result, the Schelling result, those would have to map to this guy. But our work doesn't give you anything like that. Other questions? I guess I can answer your question in sort of a silly way, which is like the codimension can be measured by the dimension of the moduli of the high structures you get in the limit. And you can often compute it and get that it's very high codimension. We say a little bit about that, but in total generality, I don't know if I can say. Okay, so you can at least hope to get like sort of a compactification in Griffiths transverse directions, such that it pulls back a compactification for any period map. No one knows how to do that, and it seems that it's unlikely to exist, but from my understanding, it's not totally clear whether that exists. Okay, and this conjecture is sort of an upgrade. The theorem we have is sort of an upgrade of a conjecture made in the work of Green, Griffiths, Laza, and Robles, and also in follow-up work by Green, Griffiths, and Robles, who had a lot of sort of important prior work that we use in our proof about, which we're going to call the Griffiths semi-ampleness conjecture. And it's the following. So suppose you have a log smooth x and x bar and some variation of Hodge structures on x. And for the experts in the audience, I'm going to assume everything is unipolar monodromy on the boundary, just to simplify life a little bit. Then you can look at this Griffiths bundle that I described last time. It's known because the FPs extend, but the Griffiths bundle also extends to the compactification. And moreover, you can describe the restriction of the Griffiths bundle to any stratum in the boundary as the Griffiths bundle of the sort of graded Hodge structures you get in the boundary. So it's got this nice persistency property. And the theorem, which was originally conjectured in this work, is that the Griffiths bundle is semi-ample.
On X or X bar?
On X bar, of course. Thank you. On X bar. So one way to think of, oh my God, I'm sorry, but quality has dropped starkly. You can tell with the lecture. The semi-ampleness on X of WGR, so the fact was cancelled out in some sense. The semi-ampleness on X is actually equivalent to the periodicity, to the algebraicity of the period element that I talked about last time. You can talk about which quality dimensional curves are contracted in terms of the Hodge theory. They're exactly the guys on every stratum on which all of the graded pure variations are constant. And if you look at the map from the projectivized Laprouge of this semi-ample bundle, it gives you some space that you map to, then it actually ends up being the Stein factorization of this map to the Baily-Borel. So in some sense, to make the Baily-Borel, you first prove semi-ampleness, and then you have sort of a finite step down to go in order to get the actual Baily-Borel quantification. But this is sort of, a crucial step in constructing the Baily-Borel. X, so yeah, this should be X bar, and then the semi-ampleness on X is equivalent to the algebraicity of period X, or the list of tangles. Okay, other questions?
It's normal.
So this guy is normal because it's on. Yeah. Is X Baily-Borel normal? No, definitely not. Yeah, we can have. I mean, think about AG for example. Right? Like you have non-normal things inside of it. And if your period image is non-normal, then you want to be normal. Yeah. But if your period image is normal, then the Baily-Borel will also be normal.
Okay.
So the Baily-Borel is sort of as normal as it can be, given the singularity of the period image. So I was solving your question. One thing that we thought about a bit that ended up abandoning because it both seemed not that natural and kind of tricky is if you had the AG Baily-Borel modification, you can take something inside AG, close it up inside AG Baily-Borel, and then try to interpret that much theoretically. It was very close to this, but with slightly different singular behavior in the boundaries. So you could try to recover something like that in this world, but we couldn't figure out exactly what it should be. This seemed like a more natural theorem. Okay, let me talk about some geometric applications to Calabi-Yau variations.
Jacob,
Yes.
can I just ask one question about the previous slide?
Yep.
But feel free to avoid the question. Is that you when you have your original family?
Yes.
That used to make the period. Well, when you have your original family, you used to make the period morphism.
Yeah.
It has like some monodromy group.
Yes.
Can you say anything about which part of in this picture, which part of the monodromy group is accounted for by this boundary?
Oh, I see.
Right, is this a very nice picture?
Right. Yes, you can do that. You can understand. You can do that even before our work. Like essentially, if you look at the boundary, there's a similar parabolic you can define in terms of the weight filtration, and it plays the exact same role here as it does. Yeah. Okay. So a concrete geometric application, part of the motivation for the work is to Calabi-Yau variations. So X is strict Calabi-Yau for those of us in the audience that aren't in the field. If its canonical bundle is trivial, and it has no differential forms of a degree between 0 and n. And the moduli of Calabi-Yau's are natural to study in the context of Hodge theory because they all have their deformation theory has immersive period maps. So in line with this, we're going to define a Hodge structure to be Cy, modeled after the strict Calabi-Yau case, if the highest filtered piece in the Hodge filtration, so the lowest dimensional piece, the Hodge filtration is dimension 1. It's a line bundle, and we call this the Hodge bundle and call it omega Cy in honor of Calabi-Yau variations. And one thing to observe is that in some sense, this generalizes the Griffiths bundle, because if you take a variation and take this tensor of wedge powers, which is sort of clearly made to make each piece subsequently one-dimensional, then the Griffiths bundle of the original variation is the Hodge bundle of this, tensor wedge variation. So this is a more general case than the Griffiths bundle case. And we have the following theorem. If you have a geometric family of strict Calabi-Yau varieties, and you look at this Hodge bundle, then its extension to any log smooth compactification is semi-ample. I would like you all to pause and now understand that it's also true for arbitrary Cy variations, but it's not true for arbitrary Cy variations. There are counterexamples. There are two important conditions that they have to satisfy, which we're going to call torsion combinatorial monodromy and integrability, which I'll say something about in a minute. And a theorem will prove that's based on this work and a bunch of other work is that in a minimal model program, the B semi-ampleness conjecture is true, which I'm going to say very little about out of understanding, but it's semi-ampleness of some moduli part divisor that shows up naturally in the minimal model program. Okay, so maybe I should stay for a second. Any questions about this theorem for those who know about Calabi-Yau's? Okay, so let me talk about these two ingredients, the torsion combinatorial monodromy and the integrability, show up in both of our cases. So what's the enemy? What's the kind of thing that we don't want to happen? Well, think about a nodal curve C, which is just a bunch of P1s glued together in nodes in some sort of chain. And you can have a line bundle on C and assume that it's trivial on each P1, or equivalently trivial on the normalization. Then at each node, once you pick a trivializing section on each P1, you can get a constant, which is just measuring how far off sort of the gluing is for your two sections. And then if you multiply all your constants around the cycle, you get some number. If this number is 1, your L is trivial on the actual curve. If it's a root of unity, your L is semi-ample. If it's not a root of unity, then it's not. Okay? So this kind of phenomenon can happen on nodal curves. And in our setup, where you have this sort of log smooth compactification and Cy variation, the enemy is if in the boundary you have a nodal curve that sort of winds around different boundary strata. If you're in a single boundary strata, you sort of have a single period map, and that's okay. The Hodge theory takes care of that. But if you vary between different boundary strata, then you kind of have to keep switching which period map you're looking at. And in theory, you could have some kind of chain of curves where your Hodge bundle or your Griffiths bundle is trivial on each individual curve, but has non-trivial monodromy as you go around the cycle. So this is a kind of thing that you have to avoid. And if you're, so if in order to be semi-ample in particular, this can't happen, and so you have to have torsion combinatorial monod. Torsion referring to this root of unity that you have to get over here. Okay, so that's what that is. Let me say something about the proof of torsion combinatorial monodromy. So in the Griffiths bundle case, this is entirely due to Green, Griffiths, and Robles. And so what's the problem? Well, the problem for us is that even though as you go around this chain of curves, you preserve a Hodge structure, the Hodge structure doesn't change. These boundary pieces don't have a canonical polarization. You sort of have to use the information of how you approach the boundary in order to get a polarization. And as you switch boundary components, that can flip. If you had a polarization that was preserved, then you'd be fine, because the automorphism groups of polarized Hodge structures are finite, just like for abelian varieties. But in the unpolarized case, that's not true. So the trick is the following. What you observe is that this is not a precise statement, because I'm in the wrong categories, but I didn't want to make it precise. You observe there's a conjugate self-duality on the Griffiths bundles whenever this kind of situation occurs. And it's precisely because you have the Griffiths bundle, and it takes into account all the different weight pieces. There's some duality there, which you can massage to get something like this. And so consequently, what you show doing some linear algebra is that even though the polarization is not preserved on the smallest, on the entire Hodge structure, a polarization is preserved on the smallest Hodge structure containing the Griffiths bundle. And you only care about the Griffiths bundle until this is enough to get what you want. So it's this really, really nice argument. In the strict Calabi-Yau case, I'm going to say very little because I know very little. But the point is that as you go to the boundary, you sort of still have boundary Calabi-Yaus, these sort of sources that occur, and you can identify the Hodge bundle on the boundary as the Hodge bundle of these Calabi-Yaus. So you still have this geometric interpretation of these sources, and you have these P1 linking results, the Kolar and a bunch of other people, which sort of tell you that this is basically canonical. And so since you have this geometric interpretation, you sort of end up showing that you do have a polarization preserved up to monotone. So that's how you handle this bit. Integrability is something which is immediate for the Griffiths bundle, but not so much for the Hodge bundle. It basically tells you that on the interior, the whole point is you have this immersive Kadara-Spencer map. So if the Hodge structure is changing at all, then your deepest piece, the Hodge bundle, must also be moving. And so the integrability condition is that on the boundary, this is also true. If you look at the smallest variation containing your Hodge structure, then if that's changing, the Hodge bundle must also be changing. I didn't write this precisely. I'll keep it like this. So yeah, you don't require it on the entire boundary, just on the small substructure containing the Hodge bundle. But the Griffiths bundle is free, and for the strict Calabi-Yau, it followed using work of Ambro and a bunch of other people as well. Okay, so let's get back to the Baily-Borel. I want to describe how we build this space. Do a quick check of time. Great. So to build H. Baily-Borel as a topological space, it's sort of not particularly difficult, or it's been known for a while. But the trick is once you have it as a topological space, you have to give it an algebraic structure, and really the difficult part is to give it a holomorphic structure as a sort of piece of your glue again. And the way that this is done is you basically find your local coordinates using the group theory, motivated by Hodge consideration, but the group theory explicitly gives you these coordinates. And I wanted to give you a couple of examples. One you probably already know. So at infinity, if you compactify the modular curve, you need something invariant by z goes to z plus 1, and so you use q, e to the 2 pi I z. This gives you a holomorphic coordinate. Everything's good. Okay, so I hope this is correct. I couldn't find this, and ChatGPT wasn't helpful. So I had to work it out myself. And I think it's right, but if it's wrong, please let me know. If you look at the case of Euclidean surfaces even, so A2, then you have two different types of boundaries. You have the Y1 boundary, and you have the sort of hyperdegenerate cusp at infinity. If you're on a rank 1 point, then what happens is that Q11, or equivalently Z11, stays bounded, and you can change coordinates to make that stay bounded. That becomes your elliptic curve coordinate. And the other guys are going to infinity. So the group you have to be variant by is you can take Z11 and Z22 and add integers to them, or you can make this operation, which sort of conjugates the whole thing by a unipolar. So it fixes Z11, it sends Z12 to Z12 plus Z11 and Z22 to this thing. And then you can just by hand sort of make your functions. Z11 is one coordinate, e to the 2 pi I determinant of Z. I think it should be over Z11 actually as a typo, but basically this is a coordinate as well. And Q22 almost works, except it changes in this way, but you have this trick, which often shows up in this theory, which is just take an average or a sum. You sum over all n, sort of the orbit of Q22 under this transformation. And the reason you're okay is because you have an n squared here that dominates, this goes to 0 super fast, the sum converges. And then in rank 2, even though things are worse, the function is actually easier. You just have any powers of q, which I'm going to index by symmetric matrices, and you take the sums by the orbit under SO2Z, and your A can be anything that's positive semi-definite. Okay, so don't have to memorize these functions. They're not going to show up again. But the point is that you have enough functions you can explicitly make using the Hodge theory of the group theory, which gives you local coordinates. And the problem is that if you work with the general period image case for general variation of Hodge structure, you don't have, well, I guess I find it hard to say you don't have that, but we can't find them, and probably you don't have them, because if you did, you could compactify B mod GZ in some sense. So you have to find your function sort of elsewhere. But let me give a sketch of the proof. So there's three steps here. Step one is to construct the Baily-Borel compactification of the period image purely as a topological space. And once we have this, it's going to be filtered sort of by the depth regeneration in this way, just like in the regular thing with a Baily-Borel set. And then we're going to show that these YKs are algebraic inductively. We know that Y is algebraic, is the smallest piece, and we're going to build this algebraization one step at a time. I want to point out that, like, one could hope to sort of algebraize this whole thing. If one could give a holomorphic structure to this whole thing at once, then one would get rid of the definable analytic machinery entirely, or one could. Because then you can apply regular Gaga, you're back in the world of compact analytic spaces. But somehow the proof is very different. The proof very much only gets to be compact at the very end of the procedure, and it's using this inductive algebraization, which, because you're not proper yet, you have to use the theory of definable analytic spaces. That's how it works. And there's two steps in making enough functions. So first of all, once you assume YK is algebraized already, you just make functions from Hodge theory, which aren't enough to give you a set of coordinates, but they are enough to give a set of coordinates on the missing, on the boundary, on the piece that you sort of haven't added yet. And then you have to add functions to give you an actual set of coordinates, and this is done from algebraic geometry. You get a bunch of functions on all of YK, which vanish at the boundary, YK plus 1, and there's none of them to embed the interior. So there's sort of two pieces. You add Hodge theory functions to give you coordinates on the boundary, and you add functions interiorly to embed the interior, but you have to be global, and so you make them vanish all along the boundary. Sorry, this piece is a little bit complicated. I haven't done the best job explaining it, but these are the two steps required to make enough functions. And then together, these give you your definable analytic structure. Gaga tells you algebraic, and you move on to the next step. At the end of the day, you get something compactly algebraic, you want to know that, and Algebraic, you basically that.
What kind of functions are these?
So I'll say something about them in a second. And if you still don't understand, then you can ask me again. Okay, so step one, constructing the Baily-Borel topological space. This part is almost immediate. There's a bit of a subtlety. So let's say you have this log smooth space, and you have this period map on the interior. Now we're going to construct the space as a quotient. So first I got to give you the equivalence relation, and you can make the equivalence relation to be the coarsest thing imaginable. On X, you sort of know what it is because you already have the map to Y. Then you close it up to get something on X bar. But the subtlety is that if you close up an equivalence relation, it's not necessarily an equivalence relation. You have to sort of compose it with itself over and over in order to get it to be an equivalence relation on the boundary as well. And the trick, the main difficulty is you have to show that this closure and this thing generated by the closure is also an equivalence relation. So the enemy is if you have to keep iterating infinitely many times. So I want to know that you stop after finitely many self-compositions.
Are you saying we can do this for any X bar? But we get to use X bar.
For any log smooth compactification? Yeah.
You don't need to
No, it's sort of, for the proof, we do a bunch of blowups and stuff, but once you know it's true on some guy, then it follows that it's true on every single compactification. Yeah. Okay, so the trick is that R preserves unpolarized Hodge structures at the boundary. Again, the polarization is sort of a subtlety, but the unpolarized Hodge structure is preserved, you can show. And then we have this lemma that generalizes work of Narasimha, Nori, and Hubrichts for the abelian variety case in the case of K3s, which is that if you take any Hodge structure, it admits only finitely many polarizations up to isomorphism. Okay? And once you have that, that sort of turns into a statement that the orbits of R individually are all algebraic, and then some algebraic geometry tells you that R itself is algebraic. And so then the stratification on the Baily-Borel compactification is just sort of induced from the stratification of X bar of the boundary by dimension. You'll notice that we're sort of using the choice of X bar in order to make the stratification down here, so it's not entirely canonical, and this is just true. We just don't know a canonical stratification, / maybe there really isn't one. We're not sure. I'm not sure. Okay, these functions. So let me talk about the Hodge theoretic functions. This is going to be a bit more Hodge theory. If you have a mixed Hodge structure, that's Cy, then I'm going to define these two other structures. So V min is the smallest substructure which contains your Cy, your deepest piece, your Hodge bundle. And then VTR for transcendental, meant to evoke the transcendental K3 lattice, is the smallest quotient of V min, one more typo, which still contains WV. So the quotient doesn't kill your Hodge bundle. And this would be a pure Hodge structure. So, okay, you can define these two things at the boundary, whatever they are. Then on a stratum, individually, you can likewise define the smallest subvariations, which contain the Hodge bundle, so they don't kill it. And then in a neighborhood of D, these are the Hodge theoretic functions. You can look at this V min variation. It has a whole Hodge structure on it on the stratum. Off the stratum, sort of weird things can happen. It has no mixed Hodge property. But you can still look at just the deepest piece, just the Hodge bundle, and this gives you a map, a local map, to projective space. The projective space of VD min determined by where this line is. And that's sort of a Hodge theoretic function, which if you work hard, you can interpret the functions I wrote on the abelian surface case as versions of this, at least some of them as versions of this. And that gives you enough functions by the integrability condition, which we had, in order to give you coordinates on the boundary. Because remember, integrability tells you that if you, on the boundary stratum, know where your Hodge bundle is, you basically know what your Hodge structure is. The Hodge structure can't move without the Hodge bundle moving. So that's the Hodge theoretic part of the construction. Yeah.
If VCY, you get these functions, then it's not.
If it's not Cy?
Then you get the function.
The question was if V is Cy, then we get these functions, and what if it's not? Are you talking about the Griffiths case? Well, we always get to the Cy case by taking this tensor of wedge powers. So we're always in the Cy case, yeah. You could probably do this without that reduction, but that reduction makes things especially clear.
And by neighborhood of D, you mean
Yeah, bar, that's right. A full neighborhood in front. Yeah.
you can say
I mean, yes, but you don't really. Sorry, yes. Yes. The question was, how do you get these functions not just on D, but on a neighborhood of D in X bar? Do we use the extension of the weight filtration to a neighborhood? And the answer is yes. We do use the fact that the weight filtration extends off the stratum. Okay. So finally, step 3, how do you get the remaining functions? Because we have enough functions to give coordinates on the boundary, but that's not enough. We need enough functions to also give coordinates on the whole local ring. And so now we're going to add a bunch of functions on the interior, which vanish on the boundary, which is kind of a nice thing to do, because you can do that sort of without knowing anything about the algebraicity yet of this thing you're trying to algebraize, right? Saying something extends as 0 is much easier than saying it extends algebraically in some way you haven't understood yet. So the setup that we have, and this already exists in the previous work on period images, it's sort of nice, it's how we algebraize a period image, is the following, which you have some algebraic space, you got some line bundle, which you can think of as some Griffiths bundle or Hodge bundle. And you assume this property that for every log smooth space whose interior maps birationally to some sub, the pullback of your bundle extends to some big enough line bundle. Okay, so this is some somewhat delicate setup, but obviously satisfied for the Griffiths bundle. And in this case, if you define vanishing sections to be global sections whose pullback for every setup like this extends as 0, then you can prove that you have lots of these vanishing sections. You have enough vanishing sections basically to give you a locally closed embedding of your space. Okay, so that's the summary of the proof. You make the Baily-Borel as a topological space, then you get the stratification, have the algebra in one step at a time, and you do this with a combination of functions coming from Hodge theory and these vanishing functions. So what are some remaining open questions in the subject. I picked some out here. So one question which I should have mentioned earlier, but forgot, so I get to mention it here, is the following question purely indefinable? Well, I guess it's not purely definable analysis, use Hodge theory. But basically, can you characterize period images without referring explicitly to the word algebraic? So if you look at this period domain, and you look at something inside it, which is closed definable analytic, and Griffiths transverse, you could make a stronger conjecture without assuming Griffiths transverse, probably, but it's tricky because you have these projective fibers I talked about last time. Anyways, if you have this kind of setup, then is V algebraic? And it's presumably enough to handle curves. Morally, that seems right, but we don't actually have a formal proof of that. In the compact case, this is true and easy, given technology. The problem is that if you imagine V is a curve, we have no idea how things degenerate at the boundary. It's not just point singularities. It could be like weird domains of analyticity type stuff going on. The definability should rule that out, but we don't know how to do that. Another question, which I really like, first sounds kind of technical, but it's the following. So we know that the Griffiths bundle now, or whatever, the CY bundle, are ample. So some power of them gives you an embedding. Is there a uniform power? So, this question could sound a bit arbitrary, but there's a philosophy of like, you want to pretend that you had a universal family, and you want to ask what would be true if you did. So if d mod gz was algebraic, there would be some power which would give you an embedding on d mod gz, and then it would work for every pullback, right?
Can you say what uniform in what? What is variant?
That's a great question. So it's related to effective, in the strict CY case, the geometric case, there's this effective B semi-ampleness, where all you fix is the dimension of the fibers, if the canonical bundle is trivial, so it's very strong. I would just ask for d mod gz to be fixed and everything else to be varying. So just the image, the target of the period map. So you fix your Hodge numbers basically. Yeah, because if you had a universal family, this would follow. So I think there's the question. No idea how to do it. The methods, don't give you any kind of uniformity. They very much refer to the original starting variety. And finally, you can ask, now that you have this Baily-Borel compactification, how it's related to other compactifications that are sort of more geometrically motivated. Ones, for example, in KSVA moduli spaces, once you make some choices, you get some geometric compactification. By universality, they presumably map to the Baily-Borel, and now you can ask the precise relationship. And that's it. Thank you very much for your attention.
Okay, thank you very much for the great series of lectures. Are there other questions? Guess everybody understands everything. So, okay, so thank you again.
Thank you.